even for open-ended questions, the models are not as diverse as we would have expected, to the point that even when you ask multiple times with higher temperature, it may not be able to vary as much. So there's intra-model homogeneity in the model output, as well as we find inter-model homogeneity, meaning, Llama, ChatGPT, and DeepSeek R1, they all have strikingly similar behavior.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I'm your host, Sam Charrington. Today, I'm joined by Yejin Choi. Yejin is professor and senior fellow at Stanford University in the Computer Science Department and Institute for Human-Centered AI, or HAI. Before we get going, be sure to take a moment to hit the subscribe button wherever you're listening to today's show. Yejin, welcome back to the podcast. It's been a while.
Oh, yeah. Thanks for having me back.
Absolutely. I think we last spoke in the fall of 2021, which seems like ages ago in AI years. I would love to kind of jump in and have you bring us up to date on what you've been working on since then. And actually, for folks who didn't catch that one, maybe start with a little bit about your background.
The time when I was on your podcast, I was still maybe best known for working on common sense, knowledge and reasoning. And back then I was also working on natural language generation quite a bit. Of course, since then, a lot has happened. So more recently, I've been excited about reasoning, especially making small language models to reason better. So I'm broadly interested in large language models, small language models, large reasoning models, small reasoning models, and then how we could make models align better for pluralistic norms and values.
Nice. What drives your interest in SLMs? Seems like a lot of the action is in large language models, and we're working hard to get the smaller ones up to the same level of performance. What's your particular interest driven by?
Yeah, so the mission really is democratizing generative AI so that it's not just companies who can purchase a lot of GPUs are able to create LLMs and adopt LLMs and serve LLMs, but also, people like myself and colleagues who are academics, so for example, cannot uh, buy as many GPUs, and is there something really meaningful and fun that we could do even with a smaller counterpart? And at the end of the day, I believe that fundamentally it should be feasible. It's only that the world has invested so much more into exploring what happens when you scale things up so much. Whereas if we invested even like smaller, even a fraction of that investment, but just a little bit more, I do think that we can unlock a lot more exciting capabilities out of small language models. Part of my research is also driven by the desire to find really better ways of teaching intelligence to machines. Currently, it's just so data centric. We can talk about that in more detail later in this podcast, but it's just so data dependent, and that's pretty much the only way we know how to teach AI about human knowledge and intelligence. But in the future, I don't know whether we will find the solution or not. But as an academics, I feel like we have to give it a try to find an entirely better solution to this that is so much more data efficient and then able to learn so much more with much less data.
When you think about how the space, the industry evolved, and your comment about where all the investment has gone. Why do you think that is? Do you feel like the investment has just kind of followed quickly what works and without uh, us taking a time to step back and identify all of the opportunities to optimize? Or do you think that there are particular impediments to smaller models that make it inherently more challenging?
There's definitely snowball effect, and then sheep herding effect. You see other sheep going where, and then you want to follow that because it's a safe choice, especially when raising funding is relatively uh, yeah, raising funding is not as hard as it used to be for AI. Therefore, that's guaranteed and proven ways of increasing intelligence. So why not? And in fact, I'm not against such effort. It's really um, interesting to see and watch how much of an intelligence scale can unlock. I appreciate that some people went crazy and find out the frontier of what happens with the scale. Having said that, I do worry about everybody trying the same thing. I think it's very important that we try different ideas, especially historically. Whatever innovation happened with computers or phones, they're always very large at the beginning, and then over the course of the time, people figure out how to make it smaller yet more powerful. So the same thing will definitely happen with generative AI as well. In fact, already there's a lot of research effort that makes models smaller but more powerful. And I think uh, we can do so much more, so much better if we put more mind and effort into it.
And how do you think about the different attack vectors or approaches to tackling this problem? And like, what do you feel like is already being explored, and where do you think there are opportunities that really haven't been explored very effectively thus far?
Yeah, so there are multiple routes. I think at the beginning, people were trying to think about compressing larger models into smaller models by either quantizing it or pruning some neurons and uh, stuff like this. So that's more like, in some sense, optimization based or a little bit more mechanical optimization based approach to making larger models to smaller models. And it does require larger models in order to make smaller models. So there's that. Nothing wrong with that. It's nice to have that option, but it's not the only way. So in the short term, I think having new architectures like some hybrid between state machines and conventional transformers like Mamba hybrid from NVIDIA, for example, could be an alternative ways of making small models more powerful. But um, there can be other ways, such as making data better, especially providing much more powerful data. And this data usually has to be at the outer skirt of the internet data, meaning the kind of data that internet couldn't quite provide in order to teach the model to do certain kinds of reasoning better. So if we have much higher quality data, usually small models learn so much faster. So that's another way.
When you say data kind of on the outer reaches of the internet, what are some examples of these sources? Like, I think it's commonly thrown around that, we found all the data that is available to the public and we train all of the large models based on this data. And, it's often proposed that the future is going to come from unlocking new types of data. For example, video, I think, is the obvious one that people talk about. Is that the kind of thing you're referring to, or do you have other ideas about what will be effective for small models?
Roughly speaking, yes. But let me clarify what I meant by better data, because internet data is not so bad, at least in terms of quantity. But when we look at the LLM pipeline, uh, pre-trained model is never good enough. despite the scale of it, pre-trained model is never good enough, and you have to do post-training on a fairly large amount of data that usually is different from the internet data. Like supervised fine-tuning as well as RL requires the kind of data points that are either curated by humans just for the purpose of teaching AI. These are not like things that you just download from the internet, but you maybe pay someone to write those data points. And the more common practice these days is that not even crowdsourcing your data, but rather hire experts like lawyers, former international math Olympiad winners. Now, these are like real experts, and then have them to write data for you. So a lot of expert data being collected as well. And then even that is not enough for AI because AI is so data dependent. So then more recently, people also do a lot of automatic synthetic data generation. Now, synthetic data, if you do it in a more like uh, in the vanilla way, just ask LLMs to write some problems for you or solutions for you, then oftentimes it's not good enough, or it could be just a repetition of the same thing. So it does require a lot more effort in the way that you uh, design prompt and then have even like a pipeline of different models making the prompt better or making the solution better, revise the solution, taking lots of iterations. So it's not as simple as just asking ChatGPT to write data for you. But if we do it quite right, then it can lead to a new data point that didn't exist on the internet. It could be like really high quality data that is uh, qualitatively different from what was on the internet. And a prime example of this is hard math solutions. So internet data does have a lot of math, but it doesn't necessarily have solutions to a lot of hard math problems. So you have to come up with those solutions, either by asking experts to write solutions for you or using LLMs in some ways in order to generate good solutions, even though they're not quite capable of doing it yet. But you could use, for example, reinforcement learning with verifiers that can explore a lot of explorations and see which solutions that AI generated happens to be correct based on the verifier. Then you collect that data, which is implicitly used as good data during RL to amplify that model behavior. But sometimes people then use that data points in order to do imitation learning on top, iteratively.
That sounds like the application of a fairly broad variety of approaches. You talk about synthetic data generation, you talk about imitation learning, you talk about RL. These are all things that historically have been like, their own field of research and then, put into practice independently. And now you're talking about integrating them together. Is that a significant element of how you think this problem gets solved, integrating a lot of these ideas?
Yes, and in fact, in some sense, the art of artificial reasoning is fairly artificial in the way that we have to orchestrate all these complex, almost like system style uh, research in order to make sure that things are done at the right time, in the right way, in the right sequence, and then iterate over and over.
Elaborate a little bit on the use of imitation learning and how you see that playing into the pipeline.
Yeah, I am blanking on which company, which model. It may have been Llama, actually. Um, uh, whose white paper describing how they did the post training may have been Llama 3. Um, they were repeating, of course, of course, they were doing something like, okay, first the pre training and then sequential fine tuning, instruction tuning, as well as like supervised training on some of the exam style data. And then finally, there's reinforcement learning phase. It's not uncommon to take the iteration between RL and SFT, such that after doing RL, you find some good behaviors, and then you want to kind of like drill on that. Here's another example. So DeepSeek R1. DeepSeek R1 does some amount of this imitation learning after the reinforcement learning, in that they do provide distilled version of their DeepSeek R1 in the smaller models. What's interesting is that they don't do straightforward RL at those small scale models, but they rather do distillation off from the stronger model that's already trained through reinforcement learning. So they say that if you just do reinforcement learning, by the way, sometimes this model starts code switching in the middle of solving math problems. It's just suddenly speaking in Chinese and English and back and forth, or some other foreign languages that may not make sense to human readers. So reinforcement learning only cares about whether you got the final solution right or not. It doesn't care about how you got there. So strange behaviors can be emergent, and then it can be even reinforced. So then, if you don't want that, if you want interpretability of the way that chain of thoughts can be interpreted by humans and verified, then you want only those chain of thought that leads to the correct solution that you like. So then you can filter out a lot of these output examples, solutions by this stronger model that went through reinforcement learning, and then collect only those better examples in order to teach smaller models. And in general, this leads to a model like purely based on imitation learning that's very powerful, but oftentimes have a better behavior that you wanted.
I guess maybe what I'm trying to get clearer on is maybe more fundamental in the sense of when I think about imitation learning, I always think of this canonical example as, you're showing a model a YouTube video of how to do something, and then the model learns how to do it based on, imitating what it sees in a video. When we try to apply that to more traditional data, textual data, it's not super clear to me how that is distinguished from just supervised fine tuning or RLHF or something like that. Like, can you explain like how they're, what makes it imitation in the application or pipeline you described?
Oh, imitation learning just means supervised fine tuning in this context. But sometimes people say imitation learning when things were performed either right before or after RL, uh, because then there's some like example trajectories that you want to imitate from, but it's really just a supervised fine tuning.
Okay.
Yeah.
Okay. Got it. We were talking a little bit about, one of the things that you might want to do is to use the model to generate synthetic data for you. And you talked about how that, tends to not work. I don't think you mentioned it, but I'm assuming we're talking about mode collapse here. And that brought to mind the artificial Hivemind paper, which was highlighted as one of the award-winning papers at this past NeurIPS, which really talked about one of the implications of this kind of mode collapse. Can you talk? It's not necessarily in the small models, thread, but can you talk a little bit about that paper and what you found interesting about it?
Sure. Yeah. So mode collapse is a real concern with LLM generation. Because so what we find in our paper is that even when you ask open-ended questions, like tell me a joke about time, or tell me something wise about time. Like when you ask, or tell me a story about something. Like When you ask these open-ended questions, you would expect that, well, there's no one good answer. Therefore, language models should be able to generate diverse set of solutions. Even when you ask, by the way, hey, give me a random number between 0 and 10, it's not
I was
random.
just thinking about that, right?
Yeah, it's usually like 7 or, 13, if you ask the bigger range. So it's not random because data is not random, or data is skewed in the first place. So when you do random of the distribution of the data, what you get is a skewed distribution. That's part one of the problem, even after pre-training. The bigger problem is after post-training, like sequential fine-tuning and RL, the output probability of the model becomes even more skewed, like zoning in to the stereotypical answers that people tend to like. And so we find that even for those questions, I mean, of course, there are questions for which you shouldn't vary the answer at all. Like, what's
Right,
the
factual questions,
factual
right?
answers?
Or
Yeah.
yeah,
You don't vary that. But even for open-ended questions, the models are not as diverse as we would have expected, to the point that even when you ask multiple times with temperature, higher temperature, it may not be able to vary as much. So there's intra model homogeneity in the model output, as well as we find inter model homogeneity, meaning, Llama, ChatGPT, and DeepSeek R1, they all have similar behavior, strikingly similar behavior. Sometimes they generate output that's almost verbatim identical, which is very strange. So that's sort of like the gist of this paper that we presented at NeurIPS, Artificial Hivemind. It's a bit of a concern to me because more and more people utilize LLMs in order to post, things on the internet. I wonder, what happens to our internet. The internet used to be the artifact of human intelligence. It really encapsulates the, vastly different ways people write and think, and it's a historical artifact of human intelligence. Now, it's really becoming the artifact of LLMs mixed with some amount of human intelligence. But what if it becomes more homogeneous and less reflecting the diverse spectrum of human thoughts? Now we're going to lose something valuable there, is my concern.
and did you study that kind of second part, the implications of this as well, or were you primarily focused on demonstrating the effect and how mode collapse works in these open-ended scenarios?
Our study stops at just like studying how homogeneous these models are, especially after post-training. Pre-trained models are better in this regard. Although this conversation reminds me of a study that I saw that looked at the language use of Reddit forums before and after ChatGPT, and they find how even Reddit posts are not as diverse as before.
There's a lot of delving now that wasn't happening before.
Yep, probably. Yep. Actually, whenever I see the word delve in anybody's writing, I'm like, what did you do?
Yeah. It's interesting that I think, folks that use a variety of LMs see this behavior a lot. Like you ask a fairly open-ended question across multiple LLMs and you get very, very similar responses. And I think, and kind of in the context of, training data, the question is often asked like, okay, so how do we improve models if models are, quote unquote, smoking their own exhaust, for example, or, training on this synthetic data? there's the implication being that we accelerate further mode collapse. But what I found interesting about this paper is that yes, there's that, but not only that, like what is the impact on the reader, the ecosystem, the humans that are in this environment where this synthetic data is being posted as articles? Is it Hivemind? Is it changing the way we're thinking? And what I think the broader thought was you're affiliated with the HAI. That seems like the place to kind of cross interdisciplinarily study this. And I'd be super interested in hearing more about that. Let me know if you hear any work in that regard.
Oh yeah. So yeah, half of my Stanford affiliation is with HAI, Human Centered AI Institute. Therefore, easily half of my research has to do with AI's impact on humanity. And I personally think that there's a lot of benefit we could get from AI, as well as concerns. So the thorny thing about this situation, current situation, is that both the benefit and potential harms coexist. And then, in some ways, depending on how we pursue AI research from here on, the future can be drastically different, is how I feel. On one hand, it could be that LLMs influence human intelligence such that we lose individuality and, we lose diversity. But on the other hand, it could also lead to a future in which the opposite is true. Or at least for some humans, I think, they might be able to become even more specialized and even more creative with the help of AI. And then for many others, they might choose to be overly dependent on AI and then lose their own thinking. And then they might just be super dependent on whatever AI says is what they say. So the gap, the best case scenario, the worst case scenario, the gap might actually increase is one possibility. In any case, I believe that it's important to be aware of potential harms and worst case scenarios in order to do something about it. So even for this problem that we find that LLMs are more homogeneous after fine tuning, as a follow up research or which was pursued concurrently to the artificial hive mind, but we haven't talked about yet is spectrum tuning. So my former student, Taylor Sorensen, he worked on this idea called spectrum tuning. It's a kind of post-training method that teaches the model to retain the spectrum of different ways of generating the output instead of just like honing in to the correct answers that were presented by the post-training data. So I do think that when we are aware of the problems, we can then try to seek solutions to that problem, either by designing new post-training algorithms and or ensuring that the post-training data is diverse in the first place, because then these data-dependent models can become less skewed than how much skewed they could have been. So I think there are a lot more future research to be done in this space in order to mitigate the potential concerns about generative AI.
When you started to describe this idea of there being two possible outcomes and that gap widening, you talked about the way we pursue research as being kind of central to which of those outcomes we tend towards. Can you elaborate on that and the role you see research having in determining direction there?
Yeah, so I do think that LLMs are doing really well on math data, math problems will necessarily be the best, more beneficial one for humanity. Now, that's one crude way of saying it, but that kind of encapsulates what I believe about the future of AI on humanity, which is that we really have to work on specific problems more explicitly. Like if we care about democracy, we then need to work on designing AI that can make humans more democratic and then be able to understand each other through democratic process and then be able to work with the different opinions through democratic process, as opposed to building AI that really optimize for people's attention and engagement with feeds that could then increase the tension among us. Because these, profit incentives are not necessarily aligned with what humanity at large should aspire to achieve. So in order to get what we want, we cannot just leave it to a few tech companies doing their wonderful jobs. I mean, I'm sure that they're all, uh, they have a lot of members in their companies uh, who have good intentions about making, well-intended people. But it could also be that easily, especially when there's like a profit competition and engagement competitions, things could unroll in a way that is not as beneficial for humanity. So when we think about how to make AI serve humans, so this is where, by the way, when I think about AI democratization, I really think about the way that I like to think about is AI of humans, for humans, and by humans. So if it's AI for humans, it should really be AI for all humans, not just some humans working for some companies in some countries. Not only that, if we're not very careful with how we design AI, I think it could be coming to a point where it's not even AI for humans, but it's more like AI for AI. And even worse, humans for AI. Humans working for AI, essentially. And for that, I think it's very important for nonprofit sectors participate in designing the future of AI, not just the profit sectors.
Part of that echoes the idea of kind of the brightest minds of our generation focused on making people click ads as opposed to, advancing humanity, science, etc. You're suggesting that there's a kind of an AI oriented aspect to that as well that we need to be on the lookout for and be proactive in defining our future.
Yeah. And more investment needed to support such research that really think about AI's impact on humanity, not just increasing the benchmark scores on math problems.
Let's come back to that. We were I think, in the middle of our small models conversation. And I think we were talking broadly about making small models perform better. But I don't recall us getting to the specifics of reasoning in small models and kind of unique characteristics of reasoning as they pertain to small models or small reasoners. Is that something you're looking at as well?
Yeah, so I'm quite excited about making small language models a better reasoner, especially because reasoning is such important intelligence capability that any model in the future has to be good at. And also this is interesting challenge because internet data doesn't really equip the LLMs to reason well right away. They can reason to some degree, but they do require a lot more post-training in order to infuse better reasoning capabilities. So my research has focused on recently how to make small models reason better. That requires both feeding in better data through sequential fine-tuning phase, and that data has to be really high quality and diverse, as well as other kinds of algorithmic approaches that can squeeze out better intelligence even from small language models that seemed kind of hopeless.
Are there any specific techniques coming to the fore with regards to the data curation side of things, or is it largely kind of manual labor in humans curating these large data sets to increase quality? What are you seeing there?
I think there's a huge future in synthetic data. So I can give you one example of our recent work called the Prismatic Synthesis. It's a synthetic data generation algorithm, which is prismatic because it acts like a little bit like a prism that can scatter the light to make it more diversified. So what we do is basically math problem synthesis, where actually it's more like math problem and solution synthesis. And we're doing this using DeepSeek R1 32 billion parameter model as the teacher model. Now, 32B parameters medium size, a little bit bigger than medium size these days, but it's much worse than DeepSeek R1, the full model, the biggest model, which is 671B parameter model. So that's like 20 times bigger than the model that we choose to use as teacher model. In this work, we primarily focus on making sequential fine-tuning data for hard math problems using this medium-scale teacher model. And then our goal is to compete against the alternative, which is to use much stronger teacher that's 20 times larger. Now, in general, that's like really difficult game to play. It's really hard to beat against a teacher that's 20 times larger because the performance gap is significant. So how on the earth do we close the gap? Is algorithmic ways of filtering the data to ensure the diversity of the generated data. Because no matter how good your teacher is, as we demonstrated in our artificial Hivemind paper, they're all repetitive. They're all homogeneous. So you have to put a lot of efforts to diversify them. The way that we diversify data is we look at the gradient vector of output given input using a proxy model, small scale proxy model. It's so small. It's only 1.5 billion parameter model. We just use Quen 1.5b, just downloaded from the net. And we use it as a proxy model to compute the gradient of output given input. And these output input pairs are the synthetic data that we just synthesized using the DeepSeek R1 32 billion parameter model. So we look at the gradient representation of each data point that this teacher model generated. And then we look at how they differ from each other by looking at k-means clustering. It's an old-fashioned clustering mechanism that still works in this modern day. So we do tensorized k-means clustering to see which clusters are overrepresented and then which data points are underrepresented. We filter out overrepresented data points really aggressively. Like we throw out the vast majority of all the data that we just synthesized and then only maintain those that are unique and different from each other. And then use those data points in order to prompt the teacher model in the next round. So we iterate through this, overgenerate and then filter aggressively using gradient vectors and then overgenerate and filter aggressively until we gather 1 million data points. So it's a lot of overgeneration and filtration. And then we find that 1 million data points is actually better than the 1 million data points that you generate from the stronger teacher model, the best teacher model.
Can you talk a little bit about the kinds of prompts and responses that you're seeing in this example?
It's just some hard math problem. It's all hard math that requires a very long solution. And so, by the way, when we auto-generate all the solutions, we have no idea whether the answer is correct or not, right? So we play a bit of a trick. The trick is simple. After we generate the problem, our case is like a fully synthetic, even for the problems. A lot of other synthetic data usually relies on problems that exist on the internet, so that you only solve legit problems. But in our case, we generate the problems as well, because we really wanted to explore diverse scope of the math reasoning uh, domain. But these solutions generated for fake problems or made up problems may or may not be correct. So what we do is we ask the model to solve the same problem multiple times and then check whether the final answer is identical to each other. If not, then we worry that the quality might be bad. It's a very crude way of filtering data, but it worked well enough for our case. And I think this is a powerful method to use for controlling the quality of synthetic data without human validation.
Got it. And so what's the, I don't know if this is the right way to ask this question or if there's a better way to ask the question, but I'm trying to get a sense for you. I think you mentioned generating a data set of 1,000 points, and it's happening over multiple rounds, I guess. And I'm trying to understand like the degree to which the prompt is varied across rounds, or are you starting from like a prompt and then developing variance based, kind of some logarithmic number of variants with each round without any kind of variance of the prompt?
Excellent question. So for prompting, we show some examples. Hey, generate math problems of this kind. And so what we change through these multiple iterations of overgeneration and filtration is the examples that we show in the prompt. So the examples come from the previous iterations, so that in the hope that the models may feel more inspired when provided with newer, more different examples in the context.
And you're at each stage, are you validating the answer to the question or you're not?
We do validate whatever we decide to keep. We do validate, so that the final 1 million examples that we've synthesized hopefully have, by and large, actually correct answers. Not guaranteed.
So the core idea here is, as opposed to starting with some prompt and saying generate 1 million examples, do some, have end stages, and at each stage generate some section and kind of disperse from there. And you've found that to work well for maintaining a degree of diversity in the data set.
So this is, depending on how you view it, it's a simple idea and a simple method, which is the big benefit of this method, because the principle here is that you really want to make data that's different, qualitatively different from the internet data that's easy to generate. You really need to go to these relatively less explored regions. And then, of course, you need to make sure that the quality is reasonably good there as well. But really, it's a diversity that we're trying to quantitatively enhance in the data set production. And I think that alone can really go quite far. Like if you really cover diverse ground, then your model can perform so much better. Because at the end of the day, current day LLMs, no matter how amazing they are only as good as the data that it was trained on. So you have to show similar examples. The more similar examples, the better for whatever the model may have to deal with during test time. The way that I like to put it is that whatever is out of distribution, just make in distribution. Make sure that you make all the out of distribution in distribution. This is how generative AI works. This is how even self-driving car works. Make sure that you cover all the rows, corner cases, everything, and that should go into your training data. This is really different from how humans learn to drive. We do not need to see a lot of these corner case examples. We just deal with it, which is the real mystery of intelligence that I wish one day we will have some answers for. We're so data efficient, but right now the generative AI, the only way, under this current framework and current paradigm, is making sure that all the out of distribution becomes in distribution. However you do it, just make sure that that's going to happen. And so that's why post-training requires curating a lot of data, or even synthesizing and curating and taking some combination of the two. And then even that's not enough, therefore you do reinforcement learning at scale. Because reinforcement learning is another ways of making out of distribution in distribution by having the model to explore itself, all these other unexplored areas, make sure that it's all explored before you get into the testing phase.
Whenever I'm in these conversations that we're talking about the role of data and the idea of using varying techniques to improve the data for small or large models, it kind of brings me back to a few years ago when your colleague there at Stanford, Andrew Ng, started kind of planting this banner around data-centric AI. And as you noted earlier, like all AI is data-centric. So what does that really mean? But the idea that we're going to improve models by focusing on like how the data that's used to train them as opposed to iterating on the algorithms continues to resonate.
Yep, in that sense, we didn't go very far.
Yeah.
But we're just doing a lot more of it in a more empirically powerful way. And still more can be done. I think it's a bit disappointing when we look at the seemingly magical, generative AI frontier models from this lens. But it is what it is. And I think we can do a lot better. Even following the current paradigm. But this is recurring theme of our conversation, which is that there must be fundamentally better way of doing this. And can we find it? In some ways, the nature found a solution, which is human brain. The nature found a solution, and human brain requires so little energy. Our brain apparently use less energy than one light bulb.
And so, thus far you're proposing that one way to do this is to focus on the data, or thus far you're proposing that one way to do this is to create synthetic data that follows, a diverse and distributed pattern while still kind of constrained in quality. You are also looking at ways to incorporate reinforcement as part of the pre-training objective. Can you talk a little bit about that work?
Yeah, so that's reinforcement learning as a pre-training objective, a new paper that we recently put out. And roughly speaking, the idea is that during pre-training, the model is forced to be completely passive in the way that it learns to predict which token comes next. But what if we encourage the model to think for itself? Before predicting the next token, what if we encourage the model to think for itself by generating, something like chain of thought, and then predict next token? And then in that context, the reward, because it's reinforcement learning, we now need to think about reward. The reward could be, there could be different ways of designing this, but the key idea of our approach is to make the reward information gain of predicting next token with thought compared to without thought. So that now you have to be able to predict the next token even better than yourself predicting the next token without a thought. So, you have to learn to think better so that your next token prediction probability becomes better than your own prediction probability without a thought. So that way we encourage the model to think for itself before answering the next token. And when
you said information gain, and then you went on to say that you want the model to predict the next token better. Like when I hear information gain, I think of like maximizing surprise in the sense of you want to give reward to predictions that I don't even know how to describe it. Not necessarily better in the sense of more accurate, but better in the sense of maybe more diverse is even the way I'm thinking about it. Can you elaborate on that part?
Yeah, actually, we kind of do the opposite of diversification in this context. So, in this context, what we are trying to do is because we frame this reinforcement learning approach under the pre-training framework, in which it's all about next token prediction. So, we go with that overarching framework. So, it's all about next token prediction. But we give some RL style flavor by incorporating a reward during the last phase of a pre-training by defining reward as information gain of being able to predict next token with good thought, good intermediate thought. And then, so what we look at is the conditional probability of a next token given all the previous tokens concatenated with your own thought, compare that with the conditional probability of predicting next token and all the previous tokens without your thought. So you compare these two quantities, and then the challenge here is that you get reward only if your intermediate thought actually increase the conditional probability of predicting next token when you concatenate your intermediate thought in addition to all the previous tokens. So it's not an easy reward to get.
So not information gain with regard to the token, but information gain with regard to the thought relative to generating the tokens.
Yeah.
You just mentioned it's not an easy reward to get. Like, to what degree do you expect, like I'm hearing in there, aspects of inference, like to what degree do you expect the complexity of training to increase based on techniques like this?
Makes computation of pre-training much higher than before. So in our work, we do a lot of experiments. One experimental setting is to control the amount of tokens during pre-training with or without RLP. So if you use the same amount of token, then we use a lot more flops, as you noticed. So another empirical setting is we control for the flop so that we use way less tokens now. Of the last phase of pre-training, we use way less tokens, but we use more. We use identical number of flops. And what we found, to my big surprise, is that when you finish your pre-training in this way, even in the flop-controlled setting, the final pre-trained model does do much better after post-training. So not only, at that point in time, not only this model does better with reasoning benchmarks, of course it will do better with the reasoning benchmarks because it was incentivized to be able to think for predicting next tokens, but also not only that, if you applied the same post-training recipe, like sequential fine-tuning followed by RL, the performance gain survives such that your model now performs even better with reasoning-heavy post-training recipe. So what does this entail is it's a bit analogous to how humans, there's this critical period during which you have to acquire language, for example. And probably it's a good idea to learn math and, logical thinking reasonably early in your life as opposed to much later in life. So something like that is happening even with the pre-training that we empirically found.
Interesting. I mentioned that we would come back to this broader idea of democratizing AI before we close out. And one of the topics there that you mentioned is pluralistic alignment. Can you elaborate on what that means and why you're excited about that idea?
Yeah, so that goes to this earlier statement I made about AI of humans, for humans and by humans. So AI of humans is about the origin of AI being really humans in terms of the values, the knowledge, uh, the different kinds of norms that AI learns from should really reflect the entirety of humanity. So that's the idea. And of course, internet is not evenly reflecting all humanity. Therefore, the resulting AI is also biased in some ways. And the question is there anything we can do? So it's really hard.
De-biasing the internet for when used as training data. That sounds hard.
It's almost impossible, right? Because you cannot go back and change the history to make even number of kings and queens. Whatever happened in the humanity already happened. So you're not gonna change that.
Although, like, there, on the other hand, like, we have debiasing statistical techniques. And so if you think of your training set as just kind of a data, a data set, we have ways to debias that. The question that jumps out to me is like, what do you lose in doing so? Like, and do you lose some fundamental aspect of, the internet that, made these LLMs that we don't understand how they work?
Yeah. I don't think debiasing is the right answer. In the sense that debiasing is also impossible, but also that, sometimes you do want to maintain your own bias. For example, if you're a religious person or if you're from a certain country where you have a particular norms that you like to go by, then maybe we want to respect that. By the way, as a human, when we interact with other human beings who we know have different values, we have a way of navigate around this person such that we maintain politeness, we maintain respect, we agree to disagree, right? So to some degree, I think this is very important that AI is aware of diverse values and then be able to navigate around it, as opposed to just being completely neutral everywhere, which may not only be not attainable, but also may not be the desirable solution if we are trying to really serve different cultural norms in a respectful manner. So in my work, we think about pluralistic alignment from three different angles. There's something called overtone pluralism, distributional pluralism, and steerable pluralism. So these concepts require explanations. Maybe let's just start with overtone. So overtone pluralism means when you
In the
ask,
sense of the Overton window?
yeah. So it's like when you ask a question that's politically thorny, for example, that could have different answers, the best way might be for a LLM to just present all of them, all of the reasonable opinions as, hey, the answer is that people have different opinions. Here's one view, there's another view, and be able to include all of them as opposed to picking the majority opinion, because that marginalizes out the rest. So being able to cover all of these options. Distributional pluralism is when AI is made for more like decision-making process, where maybe AI is, doing job application filtering, or AI is answering questions have to answer questions in a more like, categorical manner. You have to choose an answer. You cannot give all of the answers. Then distributionally, the distribution of LLM answers should mimic the distribution of humans' decisions. So at each point in time, AI might be making a decision that differs from any other human decisions. However, when we look at the overall distribution, instead of going for the like the majority case all the time, which would be distributionally super skewed, the idea is that try to be more at least distributionally even compared to now, of course humans have a bias, so it's not like our distribution of decisions is necessarily fair or unbiased, right? But at least let's not get worse than that, is the idea. Now, the last one, steerable distribution is, steerable pluralism is that you are able to steer the model to different values, your moral framework or value framework, to serve your day-to-day need within the scope that's reasonable to execute this.
So, meaning in some scenarios, you might want to be more or less pluralistic in the way the model operates?
Yeah, so the model should be able to steer to any different value system that's reasonable. Of course, the question is what is reasonable, because maybe we don't want to allow the model to be steerable to support people who want to be criminal. Criminals' value system probably should be completely out, but within the reasonable, like legal, socially acceptable scope, the ability of being able to steer your model to serve your value system.
How far along are you in identifying ways to do these things beyond, identifying, the three kind of dimensions of pluralistic approaches?
So this sort of research requires both data research as well as algorithmic research. To my delight, a lot of smart academics started developing solutions for both fronts. And so there are some new algorithms that does do more pluralistic alignment for example, distributional pluralism. And other people are working on this. But one could argue that, hey, the frontier models are not so bad. So frontier models in general are better at this kind of alignment, pluralism, compared to open source models that went through less effort in terms of data curation and, like safety, guardrails and everything. So in the spirit of making smaller, especially open source models more powerful for wider accessibility, this requires more academic research to share data, make data and share data, as well as coming up with algorithmic innovations in order to get around the limitations of the data. It's still a lot of work to be done, but at least there's a community effort.
That's awesome. So we're reconnecting in the beginning of the year, beginning of 2026. Any thoughts or predictions on what you expect to see happen this year, or maybe what you're would be excited about seeing?
Yeah, I think the community efforts on small models will escalate even further. There's last year already, there has been increasing efforts for open source community, and of course now NVIDIA is also really heavily invested into supporting open source efforts, and so we will see a lot more of that. Is one obvious prediction I can make. Another one is the use of AI for science. I'm quite excited about that personally because the positive impact of AI for scientific domains can be really phenomenal. If we know how to do it quite right, then medicine and like different aspects of human life could really benefit from AI for science. And that's also a really hard intellectual challenge, because now that really requires being able to reach the knowledge that's really above and beyond the human knowledge reflected on the internet data. And the thing is, AI is only really good at learning the data that humans are able to provide. So this is a big intellectual challenge as well, and I'm very excited about pursuing further into that direction.
Well, Yejin, thanks so much for jumping back on with us and giving us an update as to what you're working on, and in particular digging into how you're approaching reasoning for SLMs.
Thanks so much for having me again.
Thank you.
Bye-bye.